Here we have an example dealing with projectile motion, but the object initially leaves at an angle. So we have a football that's punted at 25.4 meters per second at an angle of 38 degrees above the field. So then if we just sketch out a diagram, here's our field, here's the football, it leaves at 25.4 meters per second. That would be the initial velocity. It's going to travel in some curved path and eventually come down and hit the field again. Okay, so projectile motion, remember horizontal and vertical are separate from each other. So I'm going to set up my given table with the horizontal and vertical. We know the accelerations, horizontal acceleration 0, vertical acceleration negative 9.8 meters per second squared. Now, we have VI, it's neither horizontal nor vertical, it's at our angle of 38 degrees. So we're going to do some trig on it to find our VIX and our VIY values. So if I set up a triangle, 25.4 meters per second on the hypotenuse. Then the horizontal component would be VIX, the vertical component VIY, and our angle here 38 degrees. So then cosine 38 degrees, that's going to give me VIX over 25.4. Sine of 38 degrees, VIY over 25.4. So we plug into a calculator and calculate our values there. We get our VIX, 20.02 meters per second, and our VIY, 15.64 meters per second. So I'm going to fill those in on our givens table over here. Now, that's all that's given to us in the initial problem. So now let's consider part A. We want to calculate how high the ball will go. Well, up here at the top of the path, we know some additional numbers that we can use to be able to solve the problem down. So then on part A, our interval goes from the beginning to the top. With the top of the path, the ball has to stop going up to start falling back down. So this velocity, or the final velocity at the top, will be 0. That gives us 3 numbers, and that velocity is vertical, 3 numbers vertically to be able to use a motion equation. We want to calculate how high, and that would be the delta y. So then plugging into the motion equation, Vf squared is equal to Vi squared plus 2a delta y. This is going to be 0 is equal to only the vertical initial velocity, 15.64 meters per second, quantity squared, plus 2 times the vertical acceleration, negative 9.8 meters per second squared, times delta y. So then square the 15.64, subtract it to the other side, and then divide it by the 2 and divide it by the negative 9.8. That's going to give us a delta y value of 3.53 meters. And we can tell by the situation that this is going to be in an upward direction. Now, let's consider part B. Calculate how long the ball will be in the air. Well, it's in the air longer than just to get to the top. So on part B, we have to redefine our interval. Our interval now is the whole time it's in the air, so the ball has to go like that and come back down. So that means the extra numbers we used over here in part A, we can't use. So then let's figure out what else we know when the ball returns to the level where it started. Well, when it returns, It started at a certain vertical position. It's returned to that same vertical position. Delta y will be equal to 0. When it returns, since this is a parabolic curve, the initial vertical velocity that was upward there is going to exactly match the final vertical velocity the instant before it strikes the ground. However, it's going to be in a negative direction, so then that'll be negative 15.64 meters per second. That gives us more than enough numbers vertically to use the motion equation and calculate time. So I'm going to use the motion equation VF equals VI plus A delta T, remembering that this is only using vertical numbers. So then the final vertical velocity, negative 15.64 meters per second, equals VI, that would be the initial vertical velocity, positive 15.64 meters per second, plus the vertical acceleration, negative 9.8, times time. So subtract the 15.64 to the other side and then divide by the negative 9.8. That's going to give us a time of 3.19 seconds. Now, that's one way you can calculate the time. There are other ways. You could have used the interval over here with a final velocity of 0. That would give you the time to the top. And then it's a symmetrical parabola, so you could have doubled it. So there are other ways to be able to calculate that. Now, on part C, we want to calculate how far the ball will travel horizontally before hitting the field. So in part C, we want this delta x. Now, this delta x that we're calculating, we can mark on the diagram over here. So that's the same interval in B and C. So then everything we used in B still applies to part C. So then I have enough to use a horizontal motion equation with these, and then my time. I can go delta x is equal to VI delta t plus 1/2 A delta t squared, and plug in, giving us a little space here since we ran into our other equation. This is going to be delta x is equal to VI. This would only be horizontal, so that's going to be our 20.02 meters per second. Our time period for the whole interval, 3.19 seconds. The horizontal acceleration is 0. 1/2 in delta t multiplied by 0 gives us 0. So that knocks out that last term. So when we multiply 20.02 times 3.19, we get a delta x of 63.86 meters horizontally, or by the way we've drawn it, to the right. So the key difference is when you have an initial velocity that is angled, you have some trig to do, and the trig you're doing is finding the initial horizontal and vertical components of the velocity, and then you use the motion equations just like the other projectile motion problems. Ponder physics.